Somewhere in your walls right now, there is a tiny localized pressure war going on.
Oh, absolutely. Of a complete war.
Right, like plumbers and engineers are using this crazy decimal point math to artificially choke the water in your pipes. They're creating deliberate bottlenecks and, traffic jams.
Yeah, and they're doing all of this just so your living room doesn't freeze in the middle of January.
Exactly.
Yep.
While your tiny guest bathroom turns into, like, an unbearable sauna.
It is a phenomenal amount of hidden infrastructure. I mean, we walk into a room, turn a dial on the wall, hear a faint click, and just expect the space to magically get warm.
We totally do.
We just assume heating a house is a simple binary thing, right? Like on or off.
We absolutely take it for granted. But the second you look behind the drywall and step into the world of hydraulic engineering, that simple thermostat click reveals a really reticulous battleground.
It really does.
And that is our mission for this deep dive. We are unpacking a highly detailed engineering guide on autonomous heating systems for buildings.
And it is incredibly detailed.
Very. We are going to decode the complex fluid dynamics that keep our homes perfectly warm without us ever hearing a gurgle or, feeling a random cold spot.
The foundational challenge engineers face, and this is a recurring theme throughout this source material we're looking at, is a surprisingly simple physical reality.
Which is?
Water is incredibly lazy.
I loved that realization from the text. It's so true. Water fundamentally wants to take the path of least resistance.
Always.
If you give water a choice between a short, easy trip or a long, winding journey, it will take the short trip every single time.
Every time. And in a house, the source of your hot water, like the boiler down in the basement, is usually very far from the rooms that actually need the most heat.
Right, the big living rooms or master bedrooms.
Exactly. So the entire discipline of hydraulic calculations is about forcing that lazy water to travel all the way up to the furthest, coldest corner of a building, completely against its own natural inclination.
Which brings us to the starting line of this whole operation. The text talks about establishing points with stabilized available head.
Yeah, you can think of the available head as the system's pressure budget.
Okay, pressure budget.
Right. Before the water branches out into the complex maze of your home's pipes, there's a specific anchor point where the pressure is known and stable.
Like where exactly?
It might be the exit pipe leaving your individual boiler, or, say, a collector manifold hidden in an apartment closet right after a pressure regulator.
So it is the bank account for our water pressure.
That's a great way to put it.
We have a set amount of force to spend pushing this water through the house. But as soon as the water leaves that starting line, it wants to rush down the easiest pipe.
Right. The lazy water problem.
So to control it, engineers first need a way to measure its behavior, right? To put a hard number on the physical struggle of pushing fluid through a tube.
And the source material introduces a very specific mathematical toolkit for this. And it relies on two distinct metrics.
Let's get into those.
The first one is the hydraulic resistance characteristic.
Okay, let's unpack this because the text uses a massive string of mathematical units to define this.
Oh, it does. It uses the symbol S, or specifically S times 10 to the fourth power, measured in pascals per kilogram per hour squared.
Yeah, and just hearing pascals per kilogram per hour squared spoken aloud is enough to make anyone's eyes glaze over.
Fair enough.
So what does this metric, this S value, actually represent in the physical world?
At its core, the S value measures friction.
Just simple friction.
Basically, yeah.
Yeah.
It calculates the exact amount of pressure that is destroyed simply by the physical struggle of shoving a specific amount of water through a specific pipe or fitting over an hour.
So every component matters.
Every single one.
Yeah.
Every elbow joint, every rough patch inside a plastic tube, every valve, they all create drag. The S value quantifies that drag.
So it's essentially measuring the friction of a bumpy road.
Oh, I like that.
Yeah, like if you are an engineer, the S value tells you how much energy your car is going to lose just trying to drive over the potholes and the rough asphalt.
That is a solid way to visualize it.
Okay.
But then the text introduces the second metric in the toolkit, which operates on a completely different philosophy.
Right.
It is the flow capacity, which is denoted as kV.
And the text gives a great conceptual visual for this one. Instead of measuring the struggle, kV measures the sheer volume of water that makes it through a component when you apply exactly 1 bar of pressure drop across it.
Exactly. You are standardizing the force.
You're fixing the pressure.
Right. You push with exactly 1 bar of pressure, and you measure how many cubic meters of water physically pour out the other side in an hour.
Okay, so to build on the road analogy, If S is measuring the friction of the bumpy road, the kV flow capacity is like counting the number of toll booths that are open on a highway.
That makes perfect sense.
Right. You have a set amount of traffic pressure, and you are just measuring the capacity of those toll booths to let cars through.
Yeah, the kV metric is entirely about capacity under a fixed pressure condition.
So here's my question. If I'm an engineer looking at a blueprint, why on earth do I need both of these? I mean, having two entirely different mathematical metrics for the exact same piping system seems bloated. Why not just pick the friction measurement or the capacity measurement and use it for the whole building?
Because having both is basically an elegant mathematical cheat code.
A cheat code? How so?
It comes down to the physics of how pipes are actually connected in a building. Let's start with a series connection.
Okay.
This is when water flows in a single straight line. It goes through a pipe, then hits a valve, then flows into another pipe.
Like straight shot, no branching paths.
Exactly. In a series circuit, every new component you add is just extending the length of that bumpy road.
Right, adding more potholes.
So the total resistance of the system is just simple addition. You take the S value of the first pipe, add the S value of the valve, and add the S value of the second pipe. It's clean, basic math.
But what if I tried to use our toll booth capacity metric, the kV value, for a straight line?
The math becomes an absolute nightmare.
Really?
Oh, yeah. The source shows that calculating the total capacity of components in series requires this complex reciprocal equation. It involves fractions and squared numbers. It is incredibly tedious.
Okay, so for straight lines, our bumpy road friction metric, S, is the undisputed winner.
Without a doubt. But heating systems are not just straight lines. They run in parallel.
Right, you have to heat multiple rooms.
Exactly. A main supply pipe comes up from the basement and then splits off into 3 different branches to feed 3 different bedrooms at the exact same time.
And this is where the physics completely flip.
They do. When you add a parallel branch to a pipe, you are not extending the bumpy road.
What are you doing then?
You are actually giving the water options. You are opening up a brand new path. In physics terms, adding a parallel pipe decreases the overall resistance of the system because you are increasing the total capacity for flow.
Oh, I see. We are opening more toll booths.
Exactly.
Yeah.
Which means our toll booth metric, the kV value, suddenly becomes simple addition.
Wow.
If you want the total capacity of 3 parallel pipes, you just add kV1 plus kV2 plus kV3.
And if an engineer stubbornly tried to use the friction S metric for those branching pipes?
They would be staring down a horrendous complex fraction that is just begging for a calculation error.
So the toolkit isn't bloated at all.
Not at all.
Engineers are simply swapping tools to match the physical layout of the pipes. S is for straight lines, and kV is for intersections.
You got it.
Let's take this elegant math out of the textbook and see what it actually looks like inside the walls of a house.
Let's do it.
Because the source gives us a brilliant, real-world case study to see these toolkits in action.
It's a great example.
Imagine a house with an 80 over 60 degrees Celsius heating system. And we have a pressure budget, that starting line we talked about, of exactly 15,000 pascals.
Right. That is the total force our pump is providing to heat the whole home.
Now, we have a tiny bathroom very close to the boiler. It only needs a small radiator, maybe 800 watts of heat.
Which requires about 34.4 kilograms per hour of water flow.
Right. And the pipe to get there is short, only 8 meters long.
Okay.
Then, way down the hall, we have a massive living room. It has huge windows, high ceilings, and it needs a giant radiator requiring 1,500 watts.
Almost double the heat. So that's 64.5 kilograms per hour of flow.
Yes, and it takes 15 meters of pipe just to reach it.
This scenario perfectly illustrates the lazy water problem.
How so?
Because when you use the S metric to calculate the natural friction of those plastic pipes, and the text uses a standard 12 by 2 millimeter pipe with an S value of 695, the imbalance is staggering.
Oh, I bet. The text calculates that the short 8-meter path to the tiny bathroom only creates about 1,524 pascals of resistance.
Yeah, barely anything.
But the long 15-meter path to the giant living room creates over 9,400 pascals of resistance.
So think about that. We are pushing 15,000 pascals of total pressure into this house.
Okay.
The lazy water is going to hit that intersection, feel the massive 9,400 pascal wall of friction down the long hallway, and then look over and feel the tiny 1,500 pascal bump leading to the bathroom.
The water is going to flood the bathroom.
Completely. The system is in total failure. The bathroom radiator gets blasted with a massive surge of boiling water, and the giant living room, which actually needs the heat, gets completely starved.
So if I'm the homeowner experiencing this, My instinct is just to go down to the basement and install a massive industrial strength pump. Just force the water down the hall.
Which would be catastrophic.
Really?
Why? Because if you increase the overall pressure budget to force water down the long hallway, you are also dramatically increasing the pressure hitting the tiny bathroom.
Oh.
The pipes might rattle, the radiator will hiss incredibly loudly, and you still haven't solved the fundamental imbalance. The water is still lazy, it's just moving faster.
Okay, so we need a way to artificially change the physics of the house.
Exactly.
We need to make the short trip to the bathroom feel just as difficult as the long trip to the living room. Enter the hero of our story, the thermoregulator valve.
Yes. The source specifically examines a Danfoss RAN15 valve.
Which is a very specific piece of hardware.
It is a brilliant piece of mechanical engineering. It sits right where the water enters the radiator, and its entire job is to be an adjustable bottleneck.
It's the traffic cop.
Basically, yeah.
We have our 15,000 Pascal budget. The short pipe to the bathroom only eats up about 1,500 pascals naturally. So we need the Danfoss valve in the bathroom to intentionally choke the flow, to artificially burn off the remaining 13,476 pascals.
And we use our toll booth metric, the kV flow capacity, to figure out exactly how much to choke it.
Because it's an intersection.
Well, because we need to know the exact capacity to let through under a specific pressure. The engineers calculate the missing pressure, factor in the required water flow for that specific radiator, and use the kV formula to find the exact flow capacity needed to create that bottleneck.
The text notes that to burn off that massive amount of pressure for the small bathroom radiator, the kV value needs to be an incredibly restrictive 0.094 cubic meters per hour.
Very tight.
But for the big living room radiator, which needs less artificial choking because the long pipe did most of the work, the missing pressure is only about 5,594 pascals. So the kV value is a much wider 0.273.
And here's where it gets practical. The manufacturer provides a catalog that matches these calculated kV values to specific numbers on the valve setting dial.
This is the part that completely changes how you view your home.
It really does.
The text shows that the small bathroom valve needs to be set precisely at an index of 3, while the large living room valve is set at exactly 4.5.
They even allow for half steps to get the math perfect.
The precision is just wild.
It is non-negotiable.
Think about the radiator in your house right now. It has that little white knob on the side with numbers on it.
Yeah, everybody knows that knob.
I always assumed that was a volume dial, like on a stereo. Turn it to 5 for maximum heat, turn it to 1 if you are warm.
Most people do.
But it's not a volume knob at all. It is a precisely calibrated traffic cop dialed into an exact decimal point to artificially choke the water pressure by thousands of pascals. If you mess with that dial, you could accidentally unbalance the entire house and freeze out the room down the hall.
It is a delicate, invisible equilibrium. But reading through these calculations about friction and pressure drops, an obvious workaround presents itself.
Does it?
One that the source material anticipates and rigorously tears apart.
Oh, I see where you're going. Because the friction is the enemy here.
Right.
The narrow 12-millimeter pipes are causing all this resistance, so why not just rip out those narrow pipes and upgrade the whole house to wider 14-millimeter pipes?
That's the logical leap a lot of people make.
Wider pipe, less friction, water flows easier, and we don't have to rely on all these complex traffic cop valves. Problem solved, right?
What's fascinating here is that the text explicitly runs the numbers on widening the pipes, and the results reveal a massive pitfall.
Really? Why is wider worse?
It all comes down to a physical property we haven't discussed yet. Velocity.
The speed.
The actual speed. The fluid is traveling inside the tube.
Let's look at the physics of a wider pipe. Think of a fast-moving, narrow river. If that river suddenly empties into a wide lake, the water doesn't keep rushing forward at the same speed.
No, it doesn't.
It spreads out, it loses its momentum, and it slows to a crawl.
The exact same thing happens in your heating system. With the original narrow 12-millimeter pipes, the water is being squeezed, which forces it to move quickly around 0.19 to 0.36 meters per second, depending on the room.
Okay, so moving pretty fast.
But the moment the text swaps in the wider 14-millimeter pipes, the velocity in the system plummets.
By how much?
The water leading to the small radiator drops to a sluggish 0.12 meters per second.
Which honestly sounds harmless. The water is still getting there, just taking its time. Why does the speed actually matter?
Because the text points out a critical threshold in hydraulic engineering. The minimum allowable velocity in a horizontal heating pipe is 0.15 meters per second.
So our 0.12 speed in the wider pipe is technically illegal in the engineering world.
Absolutely.
What is the physical danger of going too slow?
Air.
Air.
No matter how perfectly a system is sealed, microscopic air bubbles will always exist in the water.
Right, it's just unavoidable.
In a narrow pipe where the water is moving fast above that 0.15 limit, the sheer physical momentum of the rushing water sweeps those tiny bubbles along.
Like a strong current.
Exactly. It
Yeah.
forces them through the elbows and up into the radiators where they can be bled out.
So the forward momentum overpowers the buoyancy of the air.
But when you widen the pipe and the speed drops below 0.15 meters per second, the physics change.
The current is too weak.
The forward flow is no longer strong enough to sweep the bubbles along. Buoyancy wins.
Oh no.
The tiny bubbles float to the top of the horizontal pipes. They linger, and then they start merging with other bubbles,
A tiny bubble becomes a big bubble.
which eventually forms what the text calls an airlock.
This is a terrifying concept for a homeowner. A pocket of literal nothingness, just air, becomes so large that the slow-moving water cannot push past it.
Right.
The airlock acts like a solid concrete wall inside the pipe.
It causes a total system failure. Wow. The pipe is perfectly clean, perfectly wide. The pump is running normally, but that single pocket of trapped air completely blocks the flow. The room goes stone cold.
The irony is incredible. A homeowner decides to spend thousands of dollars to upgrade their house with wider, quote-unquote, better pipes to reduce friction. And by doing so, they inadvertently slow the water down so much that an airlock forms and shuts down the entire system.
It is the ultimate Goldilocks scenario.
Not too big, not too small.
The pipes cannot be too narrow, or the friction creates an unmanageable pressure drop. But they absolutely cannot be too wide, or the water loses the momentum needed to flush out the air.
Everything has to be perfect.
The flow, resistance, the velocity, everything must be mathematically balanced on a razor's edge.
Well, we've managed to conquer the physics of pushing water through tiny tubes in the walls, but the final section of our source material throws a massive curveball.
Oh, yes, it does.
What happens when the pipe isn't in the wall at all? What happens when the floor itself becomes a radiator?
Low-temperature panel radiant systems, commonly known as heated floors, operate on a completely different set of thermodynamic rules.
The text sets up a new case study for this. We have a room that is roughly 25.3 square meters.
Okay.
Now, in a normal setup, you would just calculate the heat needed for 25.3 square meters and pick a wall radiator that fits. But with radiant flooring, there's a catch.
The big catch.
The room has heavy furniture cabinets, solid bookshelves that cover exactly 5.3 square meters of floor space.
And that changes everything, because a standard radiator works largely by convection, heating the air that circulates around the room.
Right.
But a heated floor works through direct thermal radiation. And the physical mass of that heavy furniture fundamentally interrupts that process.
You cannot just lay heating pipes under a heavy cabinet and assume the heat will eventually seep out into the room.
No, the dense material of the furniture acts as an intense thermal insulator. It traps the heat completely against the floorboards.
It creates a permanent thermal shadow.
Exactly. And the source guide is very strict about how engineers must handle this. You have to completely subtract the footprint of that furniture from your calculations.
Just ignore it completely.
Yes. You don't have a 25.3 square meter heating surface anymore. You only have an active heating area, what the text denotes as FTP, of exactly 20 square meters.
The margins just got incredibly tight. The room still requires the same amount of total energy. The text gives a 1,200 watt heating load to maintain a comfortable 20 degrees Celsius.
But now we have less floor space to deliver it.
Right. The math dictates that every single square meter of exposed floor must output exactly 60 watts of heat.
And achieving a perfectly uniform 60 watts per square meter across a floor is a phenomenally delicate balancing act.
How do they even do that?
The text highlights a constraint called the temperature drop, denoted by the Greek symbol sigma.
Sigma, okay.
As the hot water weaves its way through the massive serpentine coil of pipes under your floor, it is constantly bleeding heat into the room. So the engineers designed the system so the water only drops a maximum of 5 degrees Celsius from the moment it enters the room to the moment it leaves.
Just a 5-degree drop over all those coils?
Exactly.
Think about the physical flow required to achieve that. If the water moves too fast, it rushes through the room without having time to actually transfer its heat into the floorboards.
Right, it leaves the room too hot.
But if it moves too slowly, it dumps all its heat in the first few feet, leaving the other side of the room completely cold.
Yeah, you get a hot spot at the door and a freezing floor by the window.
So it has to flow at the exact perfect speed to guarantee just a 5-degree drop across the entire circuit.
And that flow rate has to be constantly recalculated based on the specific thermal resistance of the materials above it.
Because the floor itself is an obstacle.
Exactly.
Mm.
The text includes a variable for the floor covering itself, which they call ramdebi. A dense ceramic tile pulls heat out of the water much faster than, say, thick hardwood planks or carpet.
The text mentions the thermal resistance being 0.1 for their specific example, right?
Yeah. Every material requires a different velocity and a different pressure calculation to maintain that perfect 5-degree drop.
So what does this all mean? It completely reframes how you look at the space you live in.
It really does.
When you stand in your living room, you aren't just standing in a hollow box waiting for hot air. You are existing on top of a highly calibrated thermal grid.
That's a great way to put it.
The engineering is so intimately tied to the physical layout of the room that simply buying a new heavy credenza and placing it against the wall dramatically alters the complex thermodynamic math happening beneath your feet.
Because you are covering up an active heat source. The energy has to go somewhere, the thermal shadow shifts, and the entire room's equilibrium is impacted.
It's wild to think about the micro adjustments happening all around us. We started this deep dive looking at the macro illusion of a thermostat click.
Which feels so simple.
Right. But the reality is an invisible, continuous battle being waged against the lazy nature of water.
It is literally an architecture of mathematics hidden behind your drywall.
From the elegant interplay of the bumpy road friction S metrics and the toll booth KV flow capacities to the meticulous decimal point tuning of a Danfoss valve playing traffic cop.
All of them are working together.
Right down to the critical 0.15 meters per second speed limit that stops your entire house from choking on a tiny pocket of air.
It makes you appreciate the silent reliability of it all. You rarely ever notice it working.
So next time you are standing in your kitchen on a freezing January morning and you hear that very slight, almost imperceptible hiss from your radiator, or you step barefoot onto a perfectly warm bathroom tile, you will know exactly the level of engineering magic and the rigorous, unforgiving physics making that comfort possible.
Absolutely. And, as we look at the incredible precision required to make these legacy systems work, it does leave us with a fascinating question about the future of building design.
Oh, really? What's that?
Well, our modern homes are increasingly becoming ultra-insulated passive houses. They are so airtight and efficient that they require only a tiny fraction of the heat older buildings needed.
Because they just trap the heat so well, so the overall heating demand is plummeting.
Exactly, which means the flow of water required to heat them is also plummeting. So, will these complex, fluid-filled traffic networks spanning across entire houses eventually become obsolete, replaced by simple, localized electric elements?
That would simplify things.
It would. Or will the math just become even more impossibly precise, forcing tomorrow's engineers to balance absolute microflows of water moving so slowly they constantly battle the very laws of physics to prevent airlocks?
Wow.
Because the smaller the system gets, the harder the invisible balancing act becomes.